Daniel Keyes Moron once said, "You can have data without information, but you cannot have information without data." This statement follows the importance of data in any analysis, and it is very important to be cautious in interpreting the data, especially the cross-sectional data. This is because cross-sectional data pools heterogeneous units together for the study and hence leads to one of the major problems of econometrics associated with data issues known as heteroscedasticity. Students, I am Professor Suresh Agarwal. As we had seen in the previous module, heteroscedasticity is a violation of one of the assumptions of the classical linear regression model. It occurs when the disturbance term mu I of all the observations have non-constant conditional variance. In its presence, ordinary least squares, estimators and forecasts based on them are still unbiased and consistent, but they are no longer blue. The estimated variances and covariances of the estimators are biased and inconsistent. Hypothesis testing procedures and statistical inference are not valid anymore. Therefore, if we continue to use the OLS method to estimate parameters and to test hypotheses for a data suffering from heteroscedasticity, then we are likely to get misleading conclusions. This makes it necessary to find some diagnostic tools to check for the presence of heteroscedasticity problem. This module shall create a better understanding of all these data related issues by focusing on the tests for the presence of heteroscedasticity.
After studying this module, we shall be able to understand different diagnostic tools to detect the problem of heteroscedasticity, the informal methods to identify the problem, which are checking the nature of the problem, and the graphical inspection of residuals. The formal methods to check for heteroscedasticity, such as Spark test, White's test, Spearman's rank correlation test, Bruce-Pagan test, etc. To begin with, let's look at some of the problems which we may encounter if we ignore the problem of heteroscedasticity. OLS estimators will no longer remain efficient. That is, they will not have minimum variance. Estimated variances and covariances of the estimators will become biased and inconsistent. Moreover, hypothesis testing based on t-stats will not be right. Thus, all these problems make necessary to detect heteroscedasticity problem. So there are two ways in general to check for the presence of heteroscedasticity. The first is the informal way, which is done through graphs, and therefore we call it the graphical method. The second is through the formal tests for the heteroscedasticity problem. Let us now move on to discuss the informal methods to identify the problem of heteroscedasticity. The informal methods to identify the problem of heteroscedasticity are of two types: checking the nature of the problem, and graphical inspection of residuals. Let us now take a look at each one of them in detail. The nature of the problem is one of the simplest methods to detect the presence of heteroscedasticity. The problem of heteroscedasticity is likely to be more common in cross-sectional than in time series data. In cross-sectional data, members may be of different sizes, such as small, medium, or large firms, or we can say low, medium, or high income. In time series data, on the other hand, the variables tend to be of similar orders of magnitude. Examples are GDP, consumption expenditure, savings, etc. Because we never observe actual values for the error term, we never know for sure whether it is heteroscedastic or not. However, we can run a least squares regression and examine the residuals to see if they show a pattern consistent with the non-constant variance. This we can do by creating a residual plot in which we take the squared residuals on the y-axis and plot it against either on one or more explanatory variables or on itself. The figure shows different patterns of squared residuals plotted against explanatory variable x. Figure A shows there is no systematic pattern between the squared residuals and the explanatory variable. Thus, there is no heteroscedasticity problem. However, figure B to E shows a systematic pattern between the squared residuals and the explanatory variable. For instance, figure B shows a linear relationship between the squared residuals and explanatory variable. Similarly, figure D and E shows quadratic relationship between the two. Thus, figure B to E is depicting the possibility of heteroscedasticity in case of a multiple regression model with more than one explanatory variable. Then instead of plotting squared residuals against each explanatory variable, we can plot it simply against the estimated y. We get the same result as the previous graph shows. Now, let us now move on to discuss the formal methods to identify the problem of heteroscedasticity. Formal methods to identify the problem of heteroscedasticity are as follows: Park test, Gleiser test, White's test, Spearman's rank correlation test, Goldfeld-Korn test, and Bruce-Pagan test. Let us now take a look at each one of them in the following slides. Let's take a hypothetical example of a restaurant and get its OLS estimators. Here, Y is equal to the total income collection of the restaurant, N is equal to the number of local competitors, P is the nearby people residence, and I is the average household income of the nearby area. Now we use the Park test to check if the residuals give any indication of heteroscedasticity, as large population, which is denoted by P, cluster in nearby area might result in large error term variances. Here, in Park test, we regress the log of square of residuals on log of p, denoting the population. The result we find is that there is no strong evidence for heteroscedasticity, as the calculated t-score, which is equal to minus 0.457, is very small. After obtaining the residuals ui hat from the OLS regression, the Gletser test advises to regress the absolute values of ui hat on the x variable, that is, assumed to be closely associated with sigma I square. They use the following functional forms as shown in the above figures 1 and 2, where Vi is the error term. However, again there are some problems with the Gletser approach. As Goldfeld and Kwon pointed out, that the error term Vi itself may be heteroscedastic. And an additional difficulty with the Gletser method is that the models, such as shown in figure 2, are nonlinear in the parameters and therefore cannot be estimated with the usual OLS procedure. Gletser himself found that the first 4 of the preceding models in figure 1 give generally satisfactory results in detecting heteroscedasticity in case of large samples. Therefore, this technique is more useful for large samples and may be used in the small samples strictly as a qualitative device to get some information about heteroscedasticity. Let's discuss this model with an example. Suppose we take a data set on wages per hour rupees, education, years of schooling, and experience, that is years of job, for a large group of workers, say 500 of an industry. Then on regressing the wages being dependent variable on education and experience as explanatory variables, we get the following OLS results. The above result shows that there exists a positive relationship between the wages and education and also wages and experience. The estimated coefficients of education and experience are also significant, as captured by their t-values of 11 and 5 respectively. However, the real problem arises because of the fact that it is a cross-sectional data, that is, a sample of around 500 workers with diverse backgrounds is taken together at a given point of time. Thus, the possibility of heteroscedasticity is higher here. So we use the Gletser test by regressing the absolute value of residuals on education, that is taken as explanatory variable for the present regression. However, we can repeat this test by regressing on experience and estimated value of wage also. The above mentioned Gletser test result suggests that data suffers from heteroscedasticity, as the coefficient of education is statistically significant. Continuing with the White's test, consider a hypothetical example on wages, education, that is years of schooling, experience, that is years of job, and an IQ level of large set of workers of an industry. First, regress wages being the dependent variable on education experience, and IQ level as explanatory variables and can get the usual OLS results and obtain the residuals, as shown in the equation 1 and 2. However, with the same problem associated with the cross-sectional data, the possibility of heteroscedasticity is higher here. Then we can use the White's test by following step 3, where we regress the square of residuals on education, square of education, experience, square of experience, IQ level, square of IQ level, and then cross products of education and experience, education and IQ level, and then finally experience and IQ level. Then we compute the R square from the auxiliary equation, which is in the step 3. Finally, our test result of heteroscedasticity depends on whether this R square is greater than or smaller than the critical value from the chi-square distribution with k degrees of freedom. If this R square is greater than the critical value, then our data will suffer from the problem of heteroscedasticity. This test uses the Spearman's rank correlation method and uses the formula 1. Here, di is the difference in the ranks allocated to two different attributes of the ith individual, and n is the total number of observations ranked. It assumes yi is equal to beta 0 plus beta 1 xi plus ui, and obtain the residuals of ui hat by running this regression. In the next step, take its absolute value, that is absolute of ui hat. Then arrange both the absolute value of ui hat and xi or yi hat according to an ascending or descending order and compute the Spearman's rank correlation coefficient given previously. Finally, assume that the population rank correlation coefficient PS is 0 and n is greater than 8. The significance of the sample RS can be tested by using the t-test as shown in the formula 2 with df is equal to n minus 2. If the computed t-value exceeds the critical t-value, we may accept the hypothesis of heteroscedasticity, otherwise we may reject it. Now, let's throw more light on this test by explaining it with an example. We know by theory that a linear relationship exists between the expected return, that is EI, and risk, as measured by the standard deviation sigma of a portfolio. By using the above given data, we try to estimate EI is equal to beta 1 plus beta 2 sigma I and obtain residuals. Since the data relates to 10 different mutual funds of different sizes and investment goals, the chances of heteroscedasticity is higher. To test this hypothesis, we apply the rank correlation test. After doing some calculation and using the formula 1, we get RS is equal to 1 minus 6, 110 divided by 10 multiply by 100 minus 1. This will be equal to 0.3333. Applying the t-test given in the formula 2, we find t is equal to 0.3333 multiplied by root of 8. This is divided by root of 1 minus 0.1110. This will come equal to 0.9998. For 8 DF, this t value is not significant even at the 10% level of significance. The p value is 0.17. Thus, there is no evidence of systematic relationship between the absolute values of the residuals and the explanatory variable, which might prove that there is no heteroscedasticity. This method assumes that the heteroscedastic variance sigma I square is positively related to one of the explanatory variables in the regression model. For simplicity, consider the usual two-variable model. yi is equal to beta 1 plus beta 2 xi plus ui. Now suppose sigma I square is positively related to xi. That is, sigma I square is equal to sigma square xi square, where sigma square is a constant. Then follow the below mentioned steps. Arrange the data from small to large values of the independent variable xi. Next, run two separate regressions, one for the small values of xi and one for the large values of xi, omitting C, the middle observations, and record the residual sum of squares, that is RSS, for each regression. RSS 1 for the small values of xi and RSS 2 for the large xi's. In the next step, calculate the ratio f, which is equal to RSS 2 divided by RSS 1, which has an f distribution with n minus c minus 2k divided by 2, both in the numerator and the denominator, where n is the total number of observations, c is the number of omitted observations, and k is the number of explanatory variables. In the last step, reject the null hypothesis that all the variances sigma I square are equal, that is homoscedastic, if f is greater than f critical, where f critical is found in the table of f distribution for n minus c minus 2k divided by 2 distribution, and for a predetermined level of significance alpha. However, this test suffers from some drawbacks. It is difficult to use in situations when there are multiple explanatory variables, because then it requires rank order or arrangement of the values of all the xi's. The middle C observations are lost. Let's take a data set of 30 families on consumption expenditure in relation to their income. Suppose we suggest that the consumption expenditure is linearly related to the income, but heteroscedasticity might be present due to pooling of different income groups in the data. So now we try to detect the heteroscedasticity by using the Goldfield-Quant test. We start by dropping the middle four observations and get the following OLS regression results. Regression based on the first 13 observations. yi hat is equal to 3.4094 plus 0.6968 xi. Regression based on the last 13 observations. yi hat is equal to minus 28.0272 plus 0.7941 xi. The t-values are given. R2 is equal to 0.76681. RSS2 is given as 1536.8 and the DF is given as 11. From these results, we obtain gamma is equal to RSS2 divided by DF, which is divided by RSS1 divided by DF, which comes to equal 4.07. The critical F value for 11 numerator and 11 denominator DF at the 5% level is 2.82. Since the estimated F value, which is equal to the gamma, is greater than the critical value, that is 2.82, we may conclude that there is heteroscedasticity in the error variance. However, at 1% level of significance, we may not reject the assumption of homoscedasticity, because then the value of the observed gamma is 0.014. In the next slide, we will present the steps of Bruce-Pagan-Goldfrey or BPG test. To demonstrate this test, first consider the following linear regression model. yi is equal to beta 1 plus beta 2 x2i plus beta k xki plus ui. Also assume that the error variance sigma square is a linear function of some non-stochastic variables z's as shown in the equation 1. Now, if f alpha 2 is equal to alpha 3, so on, is equal to alpha m, and all this is equal to 0, then sigma I square is equal to alpha 1, which is a constant. Therefore, null hypothesis of no heteroscedasticity is alpha 2 equal to alpha 3 till alpha m is equal to 0. Now, to have a better idea of this method, follow the below mentioned steps. Run the above regression in the equation and obtain the residuals. Next, get the maximum likelihood estimator of sigma square, which is sigma square equal to SSE or ui hat square divided by n. Define a variable pi which is equal to ui hat square divided by maximum likelihood estimator sigma square. Now run the following regression. Pi is equal to alpha 1 plus alpha 2 z2i till alpha m zmi plus Vi. Here Vi is the residual term. Estimate the equation 2 and define it as half of SSR, that is the explained sum of squares. Now we can show that if there is no heteroscedasticity and if the sample size n increases indefinitely under the assumption that UI are normally distributed, then it is asymptotically follows the chi-squared distribution with m minus 1 degrees of freedom. Therefore, if in a regression result the computed chi-square is greater than the critical chi-square value at the chosen level of significance, then we can reject the null hypothesis of no heteroscedasticity. Otherwise, we will not reject it. Now, the next slide will finally conclude about what we have learned so far in this module. In this module, we have seen different diagnostic tools to detect the presence of heteroscedasticity. These tools are divided into two parts: informal test and formal test. The informal methods include detection of the nature of the problem and graphical inspection of the residuals. In the cross-sectional data involving heterogeneous units, heteroscedasticity may be the rule rather than the exception. The informal methods just give a clue of the presence of heteroscedasticity, and its conformity can be done by using the formal methods. The formal methods include Park test, Gletser test, White's test, Spearman's correlation test,